it's a great pleasure to have the opportunity to tell you about our research on esophageal, cervical, and prostate cancers, and we're now extending this to studies of breast cancer. We're applying a range of infrared and terahertz techniques that are based on a new accelerator that was completed a few years ago called ALICE at the Dartborough Laboratory. This is a collaboration between 4 universities and 3 hospitals. And our aim is to develop new diagnostics for these 3 diseases, and also to clarify the potential of these particular experimental techniques for studying cancer. Let me say a little bit about the accelerator. It's an energy recovery linear accelerator. It's only the 3rd of its kind in the world, and it's the only one in Europe. It's a 4th generation light source. Synchrotrons are 3rd generation light sources. And in this light source, the bunch of electrons goes round the loop only once. And this means we can keep the bunch very small, and when the bunch is smaller than the wavelength, we get a massive increase in radiation. And on this accelerator, this happens in the terahertz region of the spectrum, which I'll describe in a minute. We have something like 70 kilowatts of power, peak power, but the average power is very low. If you wanted to boil a kettle, it would take you 18 months. So it's not going to damage any of the tissue you look at. The accelerator also has a free electron laser, which works in the infrared. Yes?
Could you please use the microphone?
Oh, yes, sure. Sorry. The accelerator also has a free electron laser, which works in the infrared. And we've just installed on that a scanning near-field optical microscope, which enables us to take images of tissue with very high spatial resolution. And we're using this accelerator for cancer research, looking at extracted tissue and exploring whether terahertz radiation can be a new therapy. And you can find the accelerator described on YouTube. Let me say something about the electromagnetic spectrum. Thank you very much. Oh, thank you. So, the electromagnetic spectrum, the terahertz region, can you hear this? Yes, I can. Good, right. The terahertz region of the spectrum is between the microwaves and the infrared, so it's very low energy. And laboratory instruments can't make sources in this region. The most power you get is 100 microwatts. We have something like 70 kilowatts, which is 9 orders of magnitude. And with 9 orders of magnitude more power, even a physicist can do biology. We're taking this radiation into a tissue culture facility, cleared for work on cancer, and where we can keep cancer tissue alive in CO2 incubators. We know terahertz has applications in medical imaging. Low power sources can reveal the extent of cancer beyond where you can see visually. And there's a clinical trial underway in Guy's and St. Thomas's Hospital to see if terahertz probes during an operation can give you a better limit of where the cancer tissue is and get better clinical margins. More controversially, we're exploring whether the terahertz radiation has potential as a therapy. There are lots of good theoretical reasons why it should, and there's some experimental evidence, so we're hoping to check that out. I'd like to say a little bit about the use of the scanning near-field microscope and infrared free electron laser in diagnosing cancer from excised tissue. We're working in the infrared, where biological molecules have characteristic spectra, and if you combine this scanning near-field microscope with an infrared free electron laser, you have enough power to do chemical imaging at 0.1 micron spatial resolution. So this is subcellular and even subnuclear. Before I go on to those results, I'll just give an idea of the previous work using Fourier transform infrared, which is a diffraction limited technique, very poor spatial resolution, but it gave us the information that in esophageal cancer, the DNA concentration doubles and spreads over larger areas, and the protein concentration is reduced, and there's a much higher DNA to glycoprotein ratio than there is in normal tissue. Well, we're repeating this sort of work, but with very much higher spatial resolution. The SNOM works by shining the infrared light onto the specimen and moving a very small fiber, the thickness of a human hair, about the specimen and picking up the signal. The top image is the atomic force microscopy of a single neuron. The bottom image, taken with the SNOM, shows particular molecules on the surface of that neuron. So we get molecular resolution sometimes. This is experiments on the esophageal tissue. The top one is cancer, the bottom one is benign, and this is showing the DNA to glycoprotein ratio. Clearly it's distinctive, but that actually understates the comparison because the DNA and the protein are actually co-located. A pixel-pixel comparison understates this. You can see this here with a slide across the DNA signal and a slide across the protein signal in esophageal tissue, and you can see the DNA anti-correlates with the protein as you would expect it to. If you look at the area over which the DNA is found, then in benign tissue there's no DNA over areas larger than that of the nucleus, but in the cancerous tissue it extends over much larger areas. There's another slice through the tissue showing the anti-correlation between DNA and glycoprotein. The nice thing about this technique is that you can automate it. The pictures on the right are what we get by looking at the wavelength images and putting them together ourselves. The pictures on the left are just sent to a cluster analysis in a computer, and provided you have the algorithm right, the data comes back immediately. So you have something that you can send to a histologist as a preliminary finding. Let me finish by talking about what you can do with Fourier transform spectral imaging. This is low spatial resolution compared to the SNOM, but many more wavelengths. So the image here is at one wavelength, and behind it there are 3,000 images taken at many other wavelengths. I won't take you through the algorithm, but what we basically do is compare two wavelengths and train the algorithm by showing it cancerous tissue, and then we find two wavelengths which we can train to reveal non-cancerous tissue, and provided we choose our pair of wavelengths carefully, we can get a good discrimination. Now, there are many wavelengths to choose from, and there are good discriminators and bad discriminators. But the pictures at the bottom show what happens when you get two good discriminators. This is the visible image. This is the analysis with the good discrimination and shows that this is most certainly cancer. A control on the right-hand side shows benign tissue. So what you can see with this is there's absolutely no doubt of identifying the presence of esophageal cancer. So my conclusions are that, first of all, we need to do a lot more work on reproducibility and patient variability, but these techniques have considerable potential. If successful, we need to develop much cheaper systems for use in hospitals. We think we may be able to develop portable terahertz instruments for cancer diagnosis. The possibility of intense terahertz radiation being used as a cancer therapy, it's very controversial. It has a lot of support theoretically, but then lots of strange ideas of a lot of support theoretically. What we need is a lot more research, and we're in the process of doing that. So I'll finish by thanking an enormous team of people who, over the last 10 years, have enabled us to complete this accelerator and carry out this research on 3 different cancers, and hopefully, going forward, on breast cancer. Thank you.